So today we get to talk about the magnetic field as a centripetal force, as introduced in our last video. And so as we remind ourselves what the magnetic field force looks like, here's a diagram that I hope rings a bell. We've got a positively charged particle moving right to left in a field that's into the board, and using our first right-hand rule, we see that the force would be down towards the bottom of the page. And as we recall, not just from the last video, but hopefully also from the fall, any force that's perpendicular to the velocity of the object that is moving will tend to make that object move in a circular path. And as we know about magnetic field force, it is always perpendicular to both the velocity and the magnetic field, so it can't help but make this orange positively charged particle move in a circular path. Let's remind ourselves of the equations involved. The force is QVB sine theta. That is the equation for any force on a moving charge in a magnetic field. And since that force is also a centripetal force, remember our equation from the fall, a centripetal force is mv squared over r. Remembering that the net force is the centripetal force in this case, and it is the only force that's acting, QVB sine theta, we can see that QVB sine theta equals mv squared over r. And we can simplify that equation as we see the v's cancel, leaving just v and no v squared on one side. And since theta is 90 degrees, in this case, then the sine of theta is 1, so that drops right out of our equation, and it brings us to a solution for r. R is equal to mv over qb. So let's take a moment to admire the equation we just found for the radius of the circle that our charged object will move in if it is moving in a magnetic field. One part of that equation I hope looks familiar. How about that numerator? What does the numerator represent? But of course, the numerator of that equation is our old friend momentum, mv, right up there in the numerator. But how does that make any sense in this situation? Why would momentum matter so much to the radius? Let's think about that. Thinking back to our diagram, or one just like it, we see that the force is related to QV, B, and M does not figure into that force at all. Oops, wrong diagram. Looks like to QV, B, and M does not figure into that force at all. Oops, wrong diagram. Looks like I used my left hand by accident. Here's the real one, with V going right to left, the field going into the board. We see that we get a force towards the bottom of the board. So no matter what the mass is, given Q, given V, and given B, the force is whatever the product of those three quantities is. But if the momentum is large, that means it is hard to get that object to move off its curved path, or to move onto a curved path off of its straight line path, which would mean a small force would make it go in a circle with a huge radius. But what does it mean to go in a circle of a huge radius? Here we see a circle of small radius right here. Here's a circle of a larger radius, and here's a circle of a still larger radius. Taken to the extreme, to move in a circle of infinite radius is to move in a straight line. So if you had a large enough momentum or no force, then you would move in a straight line, of course. There's no momentum large enough to move in a truly straight line if you have any force centripetally acting on you at all. But the greater the momentum numerically as compared to the force, the closer to a straight line that you would be moving. So now let's consider again the equation for R. R equals mv over qb. If you would consider an enormous charge moving in an enormous B field, As long as V is not zero, the centripetal force will be gigantic, and a big centripetal force would mean it turns in really dramatically off of its original straight path, meaning a tiny, tiny radius, which is exactly what the equation predicts. So with a large force, we move in a tiny radius. So in a large force, we move in a tiny radius, like so. A larger force, a smaller force, would make us a larger radius, and a very, very small force would result in a very, very large radius circle. As it says on the bottom of the page, look to JupyterEd for some problems and other centripetal force topics to be discussed. And if you're preparing for the AP1 exam, I think you can expect to see quite a bit about centripetal force on that exam. Thanks for watching and have a great day.